Our topic today is optimal motion planning for industrial robots. So my main focus is that, as you can see, most of the robots, for example, in factories and so on, have certain workspace to work in it, meaning that there must be safe distance between the robots and the humans, and certain barriers that no one can get closer to the robot while it's operating, because of course you don't want to be like this guy here. And my focus and my project deals with enabling human-robot cooperation, meaning that human has to be working closely to the robot, no constraints. Yes, this is the main focus, enabling cooperation between the robot and the human. And this boils down and can be achieved by optimal motion control, because optimal motion control deals with having a certain, for example, certain current configuration for the robot and a goal configuration. And optimal motion planning deals with finding the best solution and the best path for this robot to follow. So here, for example, we have the start and the end. We have this path here, and we have another path here, and we have an obstacle here. And of course, we have many other paths. So the optimal motion control deals with finding the best and the optimum path to go from here to here. And this can be achieved, for example, by using model predictive control. This is our controller I'm using. I'm focusing on my project. And the nice thing is that it deals with constraints. So we can think of this obstacle here as a constraint. And for example, the joint maximum and the minimum angles as another constraint. So the controller deals with finding the optimum path with consideration to these constraints. So, as I said, and as it obvious from the name of the controller, it's called the model predictive control. So it has to deal with somehow accurate model for our control system. And in order to model this robot here, our IGUS robot, the model has to deal with mainly two parts, the kinematics and the dynamics. So kinematics deals with the geometric relationships between different joints, and it is divided into two parts, forward kinematics and inverse kinematics. And the dynamics deals with forces and torques in order to actuate these joints here. And the most important thing that we have to do kinematics modeling first and then go for the dynamics, because dynamics, in order to be achieved, there are many parameters and information has to be got from the kinematic model. So first we have to deal with the kinematics, and we have to deal first with the forward kinematics. So mainly forward kinematics answers the question of if each joint here moves in a certain way, how can that affect the final configuration and the position of the tool center point at the end? So I can move this joint here, but how this can affect the position of this final point here? So this is mainly the question that forward kinematics answer. And in order to formulate the forward kinematics, I followed an approach called DH parameters. So it deals with constructing different frames at each joint. And this table right here has these parameters are called the DH parameters. So it defines the relationship between each frame and the another. It can be seen here in the robot. And by getting these DH parameters, we can get transformations, matrix transformations. So for example, I have a matrix that is a function of each joint angle here. And when I say, for example, I have joint 1, 2, and 3, 4 and 5 are having an angle, for example, 30 degrees, for example, the matrix transformation tells me where is the final orientation and the position of this tool center point here. So this is the forward kinematics. And the inverse kinematics answers the opposite question, which is if I have a certain orientation and a certain position for the tool center point, what is the value of each angle of the robot? So I have to solve for each angle here in order that can achieve the given orientation and the given position for the tool certain center point. As you can see, inverse kinematics is very important for the control algorithm, because in control we deal with having desired orientations and position for the tool center point, and we need to move our joints to these angles that can achieve the desired behavior of the trajectory we are following. So this is the inverse kinematics. And once we are done with the kinematics, we move into the dynamics. So there are mainly two approaches to realize the dynamics of the robot. One called Newtonian Euler approach, and the other is called Euler-Lagrange approach. The Euler-Lagrange approach is more practical for our case because in the Newtonian approach, we have to deal with each link individually, like having the free body diagram of each link. So we have, when we study each link individually, we have internal forces included. So it is like having forces that we don't care about, but it has to be dealt with while forming our model. So it complicated. It makes the modeling process more complicated. But in the Euler-Lagrange formulation, it deals with the energy of the system. So K is the kinetic energy, and U is the potential energy of the whole system, and Q is our joint angles, and the tau here is our torques. So we have at first have a formulation of the kinetic energy of the system and the potential energy of the system, and once we do these differential relations, we have this nice formula here. This is the formula that we can reach either by Euler-Lagrange formulation or by Newton formulation. So I have mainly three parts here. This first term deals with the inertia effects of the lengths, and it is a function of the joint angles, because at different joint angles we have different configurations, and consequently we have different inertia effects for the robot. And this term here deals with the centrifugal and Coriolis effects, and the G term deals with the gravity and the weight of the robot. So because the robot has certain weight, so it has a certain load on the motor, so we have to compensate for this load. So this is what G term doing here. And generally we have different effects that we can model for the robot. For example, the inertia effects, the link weights, the centrifugal and Coriolis effects, the vibrations, because our robot is not perfectly rigid. It has some vibrations, and those who deal with the robot can see that. And we have to model also the non-conservative forces, because if I give a certain torque for the robot, it is not practical that the robot will move forever, so it has to be certain damping present. And not all these effects are measured in our robot, meaning that we don't have to model all these ones. We have to model the ones that are more obvious in our system. So this is mainly the dynamics, and this is some simulations for our for the dynamics model that I have obtained recently. I have here the joint angles simulations. Once I give certain torque for the angles, this is some graphs showing how the joints behave, and this here is showing the elasticity of the link. This is I just obtained it a few hours ago, by the way. So it shows that the robot is not perfectly rigid. Here I give some torque and some pulse actually, so that I can see the link move to a certain distance and then vibrate to this about this point until it settles down at the end. So this is the dynamic simulations, and now it's time to talk about our controller, the model predictive control. So the model predictive control, we have it present here in this block. So it directly controls the robot, and it takes measurements from the robot and also from pose estimation, because as I said, we are enabling human-robot interaction. So I has to get some measurements from some measurements dealing with the worker that's working with the robot, for example, the position of his hands and so on. So these measurements also fed to our controller, and the controller gives the optimum control to the robot, dealing with these different constraints and the measurements taken from the robot and from the human. And the model predictive control gives its control action based on something called the cost function. So this function is a function that penalizes the error, and it can also penalize the controller effort. And this function is being optimized under certain constraints. It can be inequality constraints and equality constraints. So it gives the optimum position under these constraints. And to give an idea how the model predictive control work, it is working very similar to how humans can interact in different situations. Imagine like you are driving your bike and you have an obstacle a few meters ahead. So you don't wait until you reach this obstacle and react to this obstacle you have in your face, but you interact some time before you reach the obstacle. You can change your direction in order to avoid it at the end. So this is how the model predictive control works. From the name, it can predict the future. It is something like future telling, but it uses the model we have in order to predict how the plant will behave under the control actions we are feeding into the plant. And by this prediction, it can give a path that can avoid different obstacles and so on. So this is in principle how the model predictive control work. And as you can see, we have here our MPC. It has the model inside and an optimization algorithm running. And this is our plant. So we have measured values and reference values here, and the optimum action is fed into the plant. And this slide here summarizes how the model predictive control work. We have here, these are different steps. So this is our current step. What is previous to this step is the past, and what is ahead is the future. And these are the steps in the future. We have something called prediction horizon. This prediction horizon is the maximum number of steps ahead in the future that we can simulate. So it has to be chosen carefully, because if it's too big, we have like a large computation load for the model protective control, and if it is too small, we are not able to predict, for example, colliding with certain obstacles at a certain number of steps in the future. So it has to be chosen carefully in order to compromise between these two effects. And we also have the control horizon. This is the number of steps that we have to plan our control effort in the future. Because at each step, we simulate our plan, and we also have the path of the control parameters that we are having in the future. So I'm saying that at the next step, I'm giving this control action, and the next step after that, I'm giving this control action, and so on. But the nice thing is that I'm only applying the first control action that is only one step ahead. So after I plan this optimum control action in the future, I only apply this one here, and once I step forward in the future, one step more, so this step here is becoming my present state. So I do all the calculations again and simulations again, and pick the next control action, and so on. So this is mainly our model predictive control behavior, and it's of course, as I said, dealing with different constraints. For example, I have this constraint here, which is the maximum effort for the control. It can be, for example, the maximum voltage that I can have. So yes, the nice thing, it deals with the constraints while it is optimizing the control problem. So this is, I think, what I have done so far. And further work is to finalize the robot model. This is currently the one I am working on recently, and to verify this model. And there are maybe some parameters in the model that needs to be estimated. So I have to take some real measurements data and adjust these parameters so that it can fit well with the real measurements. And also integrating this model with MPC. So I think this is the work I will be doing next weeks. And yes, that's all. Thank you.